Imagine a moment. You stand on a distant planet, a completely new sky encompassing you, its sun perhaps not our familiar sun. You look down and see a sparkling river, a soothing blue, fresh air, and feel life stirring all around. Is it a second Earth, or merely an illusion in humanity's dream? For thousands of years, humans have gazed at the night sky, wondering if we are alone in this endless universe. That question is not just a curiosity, but a profound yearning for a second home, a place that could harbor life, a replica or another version of our own blue planet. For centuries, these were mere speculations, woven tales of science fiction. But today, thanks to remarkable advancements in science and technology, we have turned this dream into a tangible hunt. We are no longer just dreaming, we are actively searching. With every distant star we can perceive, there could be countless planets orbiting it, some of which might be candidates for the coveted title of Second Earth. This hunt, driven by relentless human curiosity, has unveiled a universe far more diverse and wondrous than we ever imagined. Today, we will embark on an exciting space journey beyond the boundaries of our solar system to explore the world of planets beyond our solar system, also known as exoplanets, and follow in the footsteps of scientists in this ceaseless quest. Welcome to SpaceTime's journey of cosmic discovery, where we explore the universe's deepest mysteries. In this video, we will delve into the topic, the search for a second Earth. Don't forget to subscribe to the channel so you don't miss other exciting cosmic exploration videos. If you find this video interesting and helpful, please like and share to support us.
What are exoplanets? Simply put, they are planets orbiting a star other than our Sun. For a long time, their existence was merely a conjecture, a belief held by astronomers. It wasn't until 1995 that we had the first conclusive evidence of an exoplanet, 51 Pegasi b, a gas giant orbiting very close to its host star, 51 Pegasi. This event ushered in a new era in astronomy, completely changing how we view our solar system and its place in the universe. Before that, we used to think that our solar system was a standard model, with small, rocky planets close to the star and gas giants farther away. However, 51 Pegasi b proved the opposite, with a gas giant located very close to its host star, a hot Jupiter, as scientists often call it. The search for these distant worlds is not easy, as they are very small and overshadowed by the dazzling light of their host stars. To detect them, scientists have developed many sophisticated methods, each with its own advantages and disadvantages. The two main methods that have yielded most of our discoveries are the radial velocity method and the transit method. The radial velocity method, also known as Doppler spectroscopy, works on the principle that the parent star is tugged by the gravitational pull of its orbiting planet. This tug creates a slight wobble in the star's motion, which changes the color of the light we receive, the Doppler shift phenomenon. When the star moves towards us, its light shifts towards blue, and when it moves away, its light shifts towards red. This small change allows scientists to infer the presence and minimum mass of the planet. The advantage of this method is that it can detect planets at any orbital inclination, provided they are large enough to create a significant wobble in the host star. However, it preferentially detects large planets with masses equivalent to or greater than Jupiter orbiting very close to their parent star. Small planets like Earth are usually too faint to create a detectable signal using this method.
The transit method, the most effective method for detecting exoplanets, is performed by measuring the brightness of a star. When a planet passes in front of its host star, transits from Earth's perspective, it causes a small, temporary dip in the star's light.
This dimming is very slight, but can be precisely measured by sensitive telescopes. The duration and depth of the dimming can provide information about the planet's size and its orbital period. NASA's Kepler Space Observatory, launched in 2009, used the transit method to discover thousands of exoplanets. The Kepler mission revolutionized the field, showing that planets are common in our galaxy. It helped us realize that a significant fraction of stars host at least one planet, and many star systems have complex multi-planet structures. One of the major advantages of the transit method is that it allows us to estimate the planet's size. Furthermore, if the planet has an atmosphere, as starlight passes through that atmosphere, chemical elements in the atmosphere will absorb some of the light at specific wavelengths, creating a signature that allows scientists to analyze the planet's atmospheric composition. This is the first step in searching for biosignatures, gases that could be produced by life, such as oxygen or methane. In addition, there are other methods, such as direct imaging. This is the most challenging method because the light from the host star is often too bright, completely obscuring the faint light of the planet. However, with advanced technology like coronagraphs and adaptive optics systems, scientists have been able to directly image a few exoplanets, especially those that are large and young, still hot, emitting strong infrared light, and orbiting very far from their host stars. This method gives us the most direct view of the planet.
Other methods include gravitational microlensing, which relies on the gravitational bending of light when a star and its planet pass in front of a more distant star. This method is particularly effective at detecting planets with small masses and those far from their host stars. The astrometry method measures tiny shifts in a star's position in the sky due to the gravitational tug of an orbiting planet. Each of these methods contributes significantly to building a comprehensive picture of the diversity of exoplanets. From these discoveries, we have begun to classify different types of exoplanets. Hot Jupiters are gas giants, with masses equivalent to or greater than Jupiter, but orbiting very close to their host stars, resulting in extremely high surface temperatures. Super-Earths are rocky planets larger than Earth but smaller than Neptune. Mini-Neptunes are planets with sizes between Earth and Neptune, with thick atmospheres, potentially containing water or other volatile compounds. In addition, there are other strange and unique worlds. Ocean worlds may be entirely covered by liquid water or ice, with a deep ocean beneath the surface. Lava worlds may be so close to their host stars that their surfaces are oceans of molten lava. Eyeball planets are tidally locked planets with one side perpetually facing the star and scorching hot, while the other side is permanently dark and frozen, with a narrow, potentially habitable strip at the boundary. There are even rogue planets, worlds ejected from their parent star systems and drifting freely in interstellar space. These planets have no host star to warm them, but some may maintain warmth through geothermal energy or a thick heat-retaining atmosphere, and could potentially harbor liquid water oceans beneath thick ice layers, concealing the potential for life. The greatest focus in the search for exoplanets is finding a second Earth, a planet capable of supporting life. This concept is often associated with a star's habitable zone, also known as the Goldilocks zone. This is the range of distance from a star where temperatures are mild enough for liquid water to exist on a planet's surface. Liquid water is considered an essential ingredient for life as we know it, acting as a solvent for biochemical reactions. However, simply being within the habitable zone is not enough for a planet to sustain life. Many other factors influence a planet's habitability, including the type of host star, red dwarf, sun-like star, atmospheric composition, the presence of a protective magnetic field, and geological activity. Some planets might be in the habitable zone but have atmospheres that are too thick or too thin, or lack a magnetic field to protect against stellar radiation. We already have several promising candidates for the title of Second Earth. One of them is Proxima Centauri b, orbiting Proxima Centauri, our closest star.
This is a super-Earth located within the habitable zone of its red dwarf star. Its proximity to us makes Proxima Centauri b an appealing target for future studies, especially regarding its atmosphere and potential to support life. Another notable star system is TRAPPIST-1, a system with 7 Earth-sized planets orbiting an ultra-cool dwarf star. 3 or 4 of these planets are located within the habitable zone. The proximity and unique structure of the TRAPPIST-1 system make it a natural laboratory for studying the formation and evolution of planetary systems, as well as the habitability potential of planets orbiting red dwarf stars. Among the more Earth-like planets, Kepler 186f was the first Earth-sized planet confirmed to be located within the habitable zone of another star. It orbits a red dwarf star smaller and cooler than our Sun. Later, Kepler 452b, an Earth cousin, was discovered orbiting a Sun-like star with a similar orbital period and about 60% larger than Earth. These discoveries indicate that Earth-like planets not only exist, but may also be common in the galaxy.
However, the definition of life and habitability remains a topic of lively debate. Must life necessarily be based on liquid water and carbon, as on Earth? Could there be other exotic forms of life, based on different solvents or chemical elements, capable of existing under extreme conditions we have never considered? Carl Sagan often reminded us of the myriad forms of life in the universe, encouraging us to broaden our perspective on what is possible. Expanding this viewpoint is crucial to avoid missing subtle signs of extraterrestrial life. The search for extraterrestrial life, also known as astrobiology, is a fascinating interdisciplinary field. One approach is to look for biosignatures in exoplanet atmospheres. For example, the simultaneous presence of significant amounts of oxygen and methane in an atmosphere could be a strong indicator of biological activity, as these gases typically react with each other and need to be constantly replenished by life. Next-generation telescopes, such as the James Webb Space Telescope, or JWST, have been and continue to revolutionize this capability. JWST has an unprecedented sensitivity to analyze starlight passing through exoplanet atmospheres, allowing us to search for molecules like water, carbon dioxide, methane, and oxygen. This data is key to determining whether a planet has the right conditions for life or might even be sustaining it. Besides searching for biosignatures, we also have the Search for Extraterrestrial Intelligence (SETI) program, listening for radio signals from space that could be signs of advanced civilizations. Although there have been no clear results so far, SETI remains an important endeavor, representing humanity's hope of communicating with other intelligent beings.
The Fermi paradox poses the challenging question: if the universe is teeming with life, then where is everybody? The silence of the cosmos remains a mystery, prompting us to ponder the rarity of intelligent life or the reasons why we haven't found it yet. Are there great filters preventing intelligent life from developing to a certain extent? Or have we simply not looked in the right place? The Drake equation, formulated by Frank Drake in 1961, is a framework for estimating the number of communicative civilizations in our galaxy. Although the values in this equation are still largely unknown, it helps us visualize the necessary factors for intelligent life and guides our research. With each exoplanet discovery, we can further clarify one of the variables in this equation. Exoplanet discoveries have had profound philosophical implications. They have shaken humanity's anthropocentric view, which Nicholas Copernicus began by placing the Sun at the center of the solar system. The realization that Earth is just one of billions of other planets in the universe has introduced a new Copernican principle, suggesting that our position is not special. This does not diminish Earth's value. On the contrary, it enhances its preciousness. In a vast universe with countless planets, Earth being an oasis of life becomes even more extraordinary. As Carl Sagan said, Earth is a fragile, pale blue dot in the cosmic ocean, and the search for a second Earth underscores our responsibility to protect the only home we know. The future of exoplanet and extraterrestrial life searches is promising. The James Webb Telescope will continue to provide deep insights into exoplanet atmospheres. Extremely large telescopes currently under construction will be capable of detecting and studying smaller planets and even potentially directly imaging some of them.
Future space missions, such as NASA's Roman Space Telescope, and mission concepts like HabEx, Habitable Exoplanet Observatory, and LUVOIR, Large Ultraviolet Optical Infrared Surveyor, are being planned to directly search for and characterize Earth-like exoplanets within the habitable zone. These telescopes will be equipped with advanced technology, such as giant star shades, to block the blinding light from host stars, allowing us to get a clearer view of the small planets around them. Furthermore, ambitious projects like Breakthrough Starshot are exploring the possibility of sending laser-propelled tiny probes to the nearest star systems, such as Alpha Centauri. Although still science fiction, these ideas demonstrate humanity's ceaseless desire to transcend the boundaries of our solar system to reach distant worlds, carrying the hope of one day finding second Earths. The journey to find a second Earth is not just a scientific endeavor, but also an intellectual and spiritual adventure, reshaping our place in the universe. Each discovered exoplanet is a new chapter in the grand story of our existence, opening up limitless possibilities and prompting the deepest questions about the nature of life and the cosmos. With every star in the night sky, there could be billions of planets waiting to be discovered. Each of these planets is a hidden gem, potentially holding answers to questions humanity has asked for millennia. Will we find a second home, or at least evidence of life out there? Only time and the perseverance of science can tell. The search continues, and every small discovery brings us closer to unraveling the universe's greatest mysteries. The hunt for exoplanets has shown us that the universe is an incredibly vast and diverse place, teeming with astonishing worlds. But before we venture too far into deep space, let's take a look at a planet right in our own solar system, a planet that has been and continues to be the focus of many ambitious explorations, Mars. Does this red planet hold the key to the mysteries of life's origins? Or could it become humanity's second home in the near future? In the next video, we will explore Mars, from its harsh terrain to its potential to support life, and the extraordinary missions that have been targeting and are currently targeting this planet. Let's delve into the blues for the red planet and the fascinating stories it tells about our past and future in the cosmos. Don't forget to subscribe to the channel so you don't miss this exciting journey.